Alright then, welcome to this video. Here we're going to do a qualitative assessment of distribution fit. Specifically, we're going to focus on the normal distribution in this case, but sort of what we do is you could generalize that to many other distributions. So we're going to use file normal check. We're using data normal, sort of the data that's on the normal tab. What we're going to do is initially describe this data and then look qualitatively at its fit. So let's talk about our sample here. Let's give it a name. I'm just going to grab this data, and in the name box up here just type data. So now we've basically called our data data. All right. And if we think about describing it, let's get a sense for our sample size, number of observations, the average, the standard deviation, and the min and the max. All right, so number of observations, we use the count function for that. So count data equals average for the average data equals standard deviation of our data equals min of our data and equals max of our data. Excellent. Okay. So first check for our normal distribution is we would expect 99% of our observations to be within 3 standard deviations of the mean. Right? The mean is 10.2, the standard deviation is 0.2, so plus 3 standard deviations somewhere just over 10.8, there's our max. And minus 3 standard deviation is somewhere just below 9.8, so 9.7 something. So good, we see sort of that first qualitative check that our range is within that plus or minus 3 standard deviations we typically expect. Okay, our next step is let's just sort of qualitatively look at that distribution, right, and see if it has that sort of bell shape. And to do that, we're going to draw a histogram, right? So we want our lowest histogram bucket to be just a little bit bigger than the min, and the largest histogram bucket to be just a little bit larger than the max. So it looks like we could just sort of start here at 9.75, go up in steps of 0.5, right, all the way up to 10.85. 10.85, don't need that one. Okay, so there's our bins, or our buckets for our histogram. What we're going to do now is calculate our frequencies. So we just grab that array beside us here, that whole block of cells, equals frequency, and then of our data, and then we're going to use this guy here as our bins array. Close bracket, and then Control-Shift-Enter to calculate those. All right, while that's selected, hit on Insert Charts and do a 2D column chart. And there's our first rough take at our histogram. Let's do a little just very basic formatting by getting rid of those gaps. So right-click, Format Data Series. We're going to get rid of these gaps in our bar chart. And the other part is click on Design here, select Data, and just change this horizontal axis instead of being a count to be our bins. Okay, get rid of the title. It needs the title here. There, so there's our sort of first, or I guess our second qualitative look. So here we have our distribution. It's sort of bell-shaped. It's peaked around the mean. It's got this hump here, but other than that, it's not bad. I mean, again, it's only a sample of 139, so it's not would be perfect, but our first check is it's a fairly good sort of qualitative fit to that normal distribution. So now we're going to do what's called as a probability plot. All right, so first things first, go over to our data and sort it from smallest to largest. So data, sort, smallest to largest. All right, so here we simply just sorted that data from our min through to our max. And now what we're going to do is calculate our CDF for these guys, so our cumulative probabilities. And so normally, if we were doing this empirically, we would just have, given that we have 139 observations, each observation would have a 1 over 139 chance of observing. because we're trying to make some inference about the overall distribution, the population that is, we're going to adjust that to be, instead of being 1 over n, to 1 over n plus 1. Right, so what we're saying here is the chance of observing a value less than or equal to 9.732 is 1 over 140. Right, so again, because it's a sample, we don't have all observations, we decrease the sample probability to this 1 over 140 versus 1 over 139, just to be reflective that we have a sample. Obviously, as the sample gets bigger, then that plus 1 makes less and less significance. But if we had a sample of 10, then you'd see the difference between 1 over 10 versus 1 over 11. All right, so here we have a 1 in 140 chance of getting an observation less than or equal to 9.732, which means that for an observation of 9.763, there's a 1 in 1 over 40 plus our probability so far, right? So basically we have a 2 over 140 of observing something less than or equal to 9.763. Autofill that down, and as we get all the way down to the bottom here, we see just less than 1, because they have 139 observations, and so 139 over 140 is a probability we would get an observation less than or equal to 10.84, right? So we're basically allowing us to see some more extreme outcomes in the true population given we've got a sample. Right, so these are sort of empirically observed probabilities. Now what we can do is sort of look at the corresponding things, but through our normal CDF. Right, so here, same idea, but we're going to assume the data follows a normal distribution with these parameters, right? This mean and the standard deviation. So we can do that with our normdist function, normdist. Right, normdist. And so here is x. Here is our mean, and just lock that, F4. And F3 is our standard deviation. And comma 1, because I want the cumulative distribution function. So I want the probability that I observe something less than or equal to 9.732. Right, and so then we can autofill this guy down. Just double click. Right, so these are the empirically observed chances that I observe values less than or equal to these. These are the corresponding probabilities, but here assuming it follows a normal distribution with these parameters. Right, and so we can look down here, and so again, very similar to 99.90. Okay, and so a next second check is if we just sort of do a scatter graph of the observed CDFs versus the normal CDF. So insert scatter graph here, and we sort of see here that we have our, I'm just going to move it to the top. So just Control X and then Control V to paste it up here. And so we have, you know, it looks like a pretty straight line, right? So if we expected the observed probabilities to closely resemble our calculated ones, we would expect to see a straight line, right? The other way to look at this is we could look at a XY scatter graph, or we could plot the CDF as a function of the data, right? And we'll do this for all three of these. So now I have the data, the empirical probabilities, the theoretical probabilities, right? Insert another XY scatter graph. And so here we see, I'm going to click on it, Control X, go to the top here. Right, it's faster to cut and paste than it is to move it. Just Control V here. Get rid of the title. And again, so now we have the CDF, the sort of observed CDF is the blue dots. The orange dot is the normal CDF. We only need to go to 1 here. Format axis. Max is 1. Okay. Right, so this is the cumulative probabilities, right? So what's the probability I would observe less than or equal to 10? So the blue line, somewhere over here, 0.18 is the data-based version, and the orange guy is the theoretical-based version, right? So here we see, when we plot those guys against each other, that's almost straight. When we look at the cumulative probability, so if we estimated probabilities from the data, or if we estimated probabilities from the normal distribution, it tells us we'd kind of get the same answer, right? That's what this guy is telling us, right? So if I estimate them with the data, or if I estimate them with this theoretical norm dist function, which we used over here, we would get the same result, which tells us that, our data sort of follows a normal distribution. The nice part of that is now we can estimate values outside of our sample, right? Either above or below that, or between individual observations. So what's the probability I get something in between 10.114 and 10.116, i.e. 10.115, right? We can accurately estimate that with our theoretical function, or more importantly, we can now look at functions of our distribution, right? So what if we had, so x here is our random variable, what if y was 10 times x, or what if y was equal to x plus 5? So we could look at transformations of x using our theoretical distribution and the properties of that theoretical distribution. Right? That sort of concludes our video.